Hello everyone, welcome to my talk. My name is Kunbei Cai. I'm a third-year PhD student in the ECE department at UCF. Today I'm going to present our paper, WBP, Training Time Backdoor Attacks through Hardware-Based WBP Poisoning. This work is done with my advisor Dr. Fan Yao and in collaboration with Clemson University. Many critical applications like autonomous driving are built on deep neural network, thus ensuring the DNN security is important. Lots of studies have focused on external threats to machine learning models, such as adversarial examples and poison attacks. However, recent advances in hardware-based attacks demonstrate severe security issues in computing systems from internal threats. Such exploits can target memory structure, such as hammer, or computing logic, like the overclocking and undervolting. Pre-trained and fine-tuning paradigm has become a popular choice for lightweight model training. Specifically, in the fine-tuning process, the last layers of the model are first replaced with new ones tailored for user downstream task. The user will fine-tune the model with her own datasets. During the paradigm, state-of-the-art backdoor attacks can launch the data poisoning attack or retraining-based Trojan attacks. Meanwhile, recent studies show that the pre-trained model-based attack can generate a poisoned PTM and release it publicly. Victim users who train from this model will end up getting backdoored models. However, these attacks either require poisoned training data, model, or control of training schedule, which might be impractical when they are protected. A natural question is, would it be possible to embed backdoor during training through hardware fault injection, specifically the ZOHammer? Also satisfies the following requirement. First, without the knowledge of downstream task, then have no access to model weights during the training. Last, can be applied to various DNA architectures. WBP is our answer. The first study on hardware-based fault attacks against DNNs in transfer learning without access to downstream tasks. First, we assume a victim user downloads a pre-trained model for fine-tuning with her own dataset in the cloud. The attacker have access to the clean public model, but without access to downstream tasks. The attacker will generate a group of bit fibs based on the initial model. He will attempt to insert Trojan during victim's fine-tuning through bit flips. After user fine-tuning, we will get backdoored models. Finally, even the initial model and the dataset are clean, the downstream dataset is unknown to the attacker, we can still succeed. Here we show the naive idea as shown in this figure. For any benign input, it will generate an output representation at feature map space. The OR controls the output. Without the knowledge of downstream task, we can only get the OR of some benign publicly available samples. Our idea is here, is it possible to generate a quite different OR from the OR of any benign inputs? So that during victim's inference time, the input with triggers will get an out of domain OR, thus activating abnormal inputs, finally become a task agnostic attack. We show the detailed idea of our proposed attack, distance-aware weight-bit poisoning. The figure shows the OR space. The area with red color denotes higher gradient value with respect to distance. Prior attacks tries to move the triggered input OR distribution to this fixed OR. However, it is impossible to move them to the predefined OR via weight-bit flips because of the no gradient, which means more bits are required to move the same distance. Motivated by this, we maximize the distance between clean input OR distribution and the trigger OR distributions, along with the easiest movement direction, that is in the red area. WBP is an iterative trigger and bit search framework. Here we use MMD as distance measure to evaluate the distance between two probability distribution. The trigger loss is defined as follows. Here, M is the pre-trained model. Our goal is to maximize the distance between the triggered and the clean ORs with bit flips. For bit flip search loss, the first part is exactly the same as trigger loss, but we add one more clean loss to ensure the backdoor stealthiness. Finally, we develop a technique called progressive bit reduction to further minimize the required bit flips to maximize the average impact of each bit flips. The above table shows the evaluation results, including the number of bit flips and the attack performance for WBP. WBP can achieve a great success on both CNN and transformer-based models with an extremely high ASR of 99.6% and a negligible influence on the accuracy, about 0.2% drops. The required number of bits are only 49.6 on average, as few as 27 bits. The results show that only one bit flip set can succeed across all the downstream tasks. For WBP with progressive bit reduction, WBPR successfully maintained a comparable SR of 99.3%. Furthermore, the number of bit flips decreases significantly. There is about 56% bit flip number drops on average, with only 0.3% ASR drops. Finally, WBP is the first task agnostic fault attack during training time. In this paper, we designed a novel mechanism to maximize OR distribution efficiently. We designed a novel algorithm to further reduce the required bit flips. Experimental results show that WBP can compromise state-of-the-art scenes and vision transformers. Thanks.